Ever stop to think about what's really happening when you stream a movie, or do a quick search, or just scroll through your feed? Behind that smooth, instant experience, there's this absolute miracle going on. We're talking about massive, interconnected systems, sometimes millions of computers all across the globe, all working together in perfect harmony. They're basically the invisible engines powering our entire modern world. But how?
I mean, seriously, how do you get millions of computers to act like one giant, coherent machine? How do engineers possibly tame that kind of mind-bending complexity to build the services we rely on to be fast, secure, and always on? Well, the secret, it's not just about writing a ton of code. It's about having a plan. It's about using a special set of blueprints for this digital world, and we call them system models.
So here's our game plan for this explainer. First, we'll break down what system models even are. Then we'll look at the physical building blocks, the actual hardware. After that, we'll dive into the architectural blueprints, followed by the fundamental laws and, the hidden dangers every system faces. And finally, we'll tie it all together and see why these models are so incredibly important.
All right, Section 1. What are system models? Think about it like this. You wouldn't try to build a skyscraper without a detailed blueprint, right? You can't just show up with a bunch of steel and start welding. The same exact principle applies to these huge digital systems. The complexity is just off the charts, and you've got to worry about everything from hardware failing to network lag to actual cyber attacks. System models are the blueprints that let engineers get a handle on all that chaos. So what is a system model really? Well, at its heart, it's an abstraction. That's a fancy way of saying it's a simplified version of reality. It's designed to intentionally ignore all the tiny, nitty-gritty details of specific technologies so you can focus on what's truly essential. It gives you a clear framework for thinking about and designing a system. It's a tool for reasoning about how things should work and, just as importantly, all the ways they might break. And here's the key thing. It's not just one single master blueprint. That would be too simple, right? Instead, designers use 3 different but complementary models to get the full picture. You've got the physical model, which is all about the hardware, the actual computers and the network. Then there's the architectural model, which describes how all the software components are organized and how they talk to each other. And finally, you have the fundamental models, which deal with the core, unavoidable challenges every system has to face, like failures and security threats.
Okay, let's dig in, starting with the most tangible layer, the physical model. This is all the stuff you could, in theory, go and touch. We're talking about the computers, your phone, the servers in a data center, and the literal cables and wireless signals that connect everything. This is the foundation. And believe me, this foundation has changed in ways that are just hard to wrap your head around.
Let's take a quick trip back in time. In the late 70s, a distributed system meant maybe a few dozen computers connected on a local network, a LAN, probably all huddled in one building, sharing a printer that cost more than a car. Then, fast forward to the 90s, and boom, the internet changes the entire game. Suddenly, we're talking about internet-scale systems with countless machines all over the globe running different hardware, different software that all somehow had to play nice together. And today? Oh, today we're in a whole new era. This is the world of massive cloud data centers, billions of phones in our pockets, and the Internet of Things, where the computer isn't even on your desk anymore. It's invisibly woven into the world around us.
Okay, so we've got all this hardware. Now what? How do we actually organize the software that's going to run on it and make it do something useful? That, my friends, is where architectural models come in. If the physical model is the pile of bricks and lumber, the architectural model is the actual blueprint for the house. It defines the structure, what each part does, and how they all communicate. Now, 2 of the most fundamental patterns you'll see everywhere are client-server and peer-to-peer. Think of client-server like a central library. The library, that's the server, has all the books, all the resources. And you, the client, have to go to the library to request a book. It's the model behind most of the web. Peer-to-peer, on the other hand, is more like a book-sharing club. There is no central library. Everybody is a peer, everybody has some books, and you just trade directly with each other. It's a really powerful model because it can scale like crazy. The more people who join the club, the more books are available for everyone. And you can really see the difference here, can't you? On the left, you've got that clean, organized client-server model. All the clients are talking to those central servers, but you can also see the weakness, right? The servers can become a bottleneck, or worse, a single point of failure. On the right, the peer-to-peer network looks a lot more chaotic, sure, but it's also incredibly resilient. If one of those peers goes offline, who cares? The rest of the network just keeps on working.
Okay, here's a super powerful idea that helps manage all this architectural complexity. It's called layering. It's basically a clever form of abstraction. Think about building a house again. You have the foundation layer, then the framing layer, then electrical, then plumbing. Each layer relies on the one below it, but it doesn't need to know the messy details of how it works. The plumber doesn't need to know the chemical composition of the concrete. They just trust that the foundation is solid. This separation makes building incredibly complex things way easier.
So let's see what this layering looks like in a typical software stack. At the very bottom, you've got the hardware. Right on top of that, you have the operating system. And way up at the top are the applications you actually use. But what's that layer in the middle? Middleware. Middleware is this crucial software layer that acts like a universal translator. Its whole job is to hide the messy, complicated reality of different networks and operating systems and give application developers a single, clean way to build their software. It's a huge time saver. And this whole idea of layering leads us straight to the kinds of architectures that power pretty much every website you visit. A simple two-tier architecture just separates things into two layers, the client, which is your browser, and the server, which holds the data. But many modern sites use a three-tier architecture. Here, they split the server itself into two parts, a web server that handles all the application logic, and a separate database server that just worries about the data. This separation makes the whole system much easier to manage and scale up. Okay, we've talked about the physical hardware and the software blueprints, but now we have to get into the really deep stuff, the invisible forces that govern any distributed system. These are the fundamental models. They aren't about specific technologies. They're about the inherent, unavoidable challenges you face anytime you try to make separate computers work together. These challenges get grouped into three core models. First, the interaction model, which is all about communication, performance, and the massive headache of time. Second, the failure model, which is pretty straightforward. It's all about what can go wrong and how things can break. And third, the security model, which deals with how we protect the system from bad actors and external threats. Now this next idea, this is one of those concepts that kind of breaks your brain a little the first time you hear it. In a distributed system, there is no such thing as a single global time. On your own computer, time feels simple, but when you have thousands of computers, their internal clocks are all ticking at slightly different rates. They inevitably drift apart. And even if you try to sync them, you can never guarantee they are perfectly exactly aligned. This has huge consequences. You simply cannot rely on timestamps to know the true order of events across different machines. It's a massive problem. So that leads to a pretty scary question, right? If time is all wobbly and unreliable, and we know for an absolute fact that computers and networks are going to fail, how in the world do we build systems like banking networks or air traffic control that have to be rock-solid reliable? Well, the first step is to stop wishing that failures won't happen and start defining exactly what kinds of failures you're prepared to handle. This is exactly what a failure model is for. Its job isn't to prevent failures. That's impossible. Its job is to classify them. You have simple crash failures, where a server just stops, dead. Then you have omission failures, where maybe a message just gets lost in the network and never arrives. But the real monster, the one that keeps engineers up at night, is the arbitrary failure, also known as a Byzantine failure. This is where a component doesn't just crash, it goes completely rogue. It starts sending corrupt data, or maybe it's been hacked and is actively malicious. Building a system that can survive that is one of the hardest problems in computer science. And finally, we have the security model. This is where we put on our paranoid hats and explicitly assume there is an enemy out there, an adversary who is actively trying to break our system. This model assumes the enemy can tap into our communication channels and can copy, alter, or even inject fake messages. Thinking this way forces you to be defensive, to build in things like encryption from the very beginning to protect the system's integrity.
So let's bring this all back home. We've looked at three totally different kinds of models: physical, architectural, and fundamental. And yeah, it might seem a little abstract, a little theoretical, but this framework, this way of thinking, is what allows engineers to turn a complex idea into a real, working, robust system that we all rely on every single day.
And this is probably the single most important thing to take away from all this. These models are not competing with each other. It's not a choice of, should I use the architectural model or the fundamental model today? No. They are complementary lenses. You have to use all of them together to get a complete, accurate picture of what you're building.
So you can think of it as a logical workflow. Step 1, use the physical model. Understand your constraints. Are you building for a massive data center or for tiny, low-power smart devices? Step 2, use the architectural model. Pick a blueprint that makes sense for your problem. And finally, step 3, you have to stress test that design using the fundamental models. Ask the hard questions. What happens if this server crashes? How do we handle network delays? What's our plan for when an attacker shows up? Answering those questions is the difference between a system that just works on a good day and a system that lasts.
You know, we've seen these models evolve so dramatically. from a handful of computers in one room to billions of devices scattered across the entire planet. But the pace isn't slowing down. As we push into a future with pervasive AI, quantum computing, and even more interconnected devices, the complexity is just going to keep exploding. So it leaves us with this really fascinating question to think about. What new, unseen forces will emerge? What's the next great challenge that the system designers of the future will have to master? What will be their fundamental model?